Suppose you're in a senior machine learning infrastructure interview, and the interviewer asks you this. Our new reasoning model is great, but it uses a 2,000 token chain of thought even for simple questions like, what is 2 plus 2? This is killing our inference budget. How do you fix this without sacrificing its ability to solve complex problems? So how would you begin your answer given that the answer most people give is the one we are about to break? Models really do spend that many tokens on easy questions. Researchers at Tencent AI Lab and Shanghai Jiaotong University asked a reasoning model what 2 plus 3 is, and it wrote out 13 separate solutions and spent 901 tokens before it settled on 5. A million requests like that in one day costs roughly $1,800, and that money goes on questions a pocket calculator answers for free. That is why the first answer most people reach for is to stop asking a single model to handle both the easy questions and the hard ones. Instead of one model doing both jobs, you keep two, a small fast model for the easy questions and the big reasoning model for everything else, with something in front of them deciding which one receives each request. This is a serious answer and not a beginner's mistake. GPT-5 is built this way with a router in front of several models that picks one for each message in real time, based on what kind of conversation it is, how complex it looks, and whether any tools are needed. When our request runs through that router, it looks like a clean win, because what is 2 plus 3 goes to the small model and 901 tokens drops to single digits. So what does the router have to know in order to pick a model, and when does it have to know it? It has to know how hard a request is before anyone has tried it, and for a lot of requests, judging that is almost as hard as just doing the work. Here are two requests that are worded the same way with one number changed. Is 97 a prime number and is 91 a prime number? Both look easy, so anything judging them by how they are written would treat them the same way. And yet 97 really is prime, while 91 is 7 times 13, which you only find by doing the arithmetic rather than by reading the words. So routing has not removed the hard judgment. It has moved that judgment to the router, which now has to reach the same conclusion the model would reach without doing any of the work first. And when the router picks wrong, nothing reports an error, because the small model answers with full confidence and no later step checks whether it was the right model to answer. On the day GPT-5 launched, its autoswitcher broke, and Sam Altman said the result was that GPT-5 seemed way dumber. That was an outage rather than a misjudged request. So the only thing it shows is that a router's failures reach the user as a vague drop in quality with nothing to say what went wrong. If you build a router yourself, the number to watch is how often it calls a request easy when the large model gets it right and the small one gets it wrong. None of this makes routing a bad idea everywhere because it is worth using when two models really do differ in what they can do or what they cost. In this case, they do not differ, and even a perfect router still means keeping two sets of weights for one capability. So can both behaviors come from one model instead? They can, and Qwen 3 does it in the third of its 4 post-training stages in a step called thinking mode fusion. It takes a model that has already been trained to produce long reasoning and puts the non-thinking behavior back into it by continuing to fine-tune on a mixed dataset where the thinking examples are the model's own good long chains of thought filtered by rejection sampling, and the non-thinking examples are picked by hand across coding, maths, translation, and roleplay. Both halves come out of the same model family, and that is what matters here because the model is not being taught two skills. It is being taught to follow a flag. The flag itself is simple. You write /think or /no think into the user prompt or the system message. You can change it from one turn to the next, and the model follows whichever instruction came last. So the architecture is now much smaller. One set of weights, one allocation of memory, nothing in front of it, and what is 2 plus 3 arriving with the no think flag attached. To know whether that worked, you would measure output tokens per request in each mode and accuracy on hard held out problems in thinking mode. Because if the fusion left the reasoning weaker, you're back to needing two models. That still leaves one question unanswered. Who sends the flag? Somebody still has to decide which mode this request gets before the model generates a single token, and that is the same question the router was asking. How hard is this one? The question has not gone away, and all that changed is who has to answer it, which is no longer a classifier but whoever is sending the request. The flag is still worth having because the second model is gone, the second allocation of memory is gone, the classifier is gone, and the caller usually does know more about what a request is for than a classifier could work out from the words alone. But it matters which kind of game that is. It got cheaper, and it did not get easier. The router and the flag sit on the same side of one line because both of them need somebody to guess how hard the request is before any of the work has started. There's only one way off that line. What if the decision does not have to be made in advance at all? Then you do not make it in advance. You set a limit on how many tokens the model can spend on thinking, and when it reaches that limit, the thinking is stopped and a line is written into the model's own output. The line reads, considering the limited time by the user, I have to give the solution based on the thinking directly now, followed by the tag that closes the thinking block, and the model then writes its answer using only the reasoning it had reached before it was stopped. Something has just changed. The decision about how much to think was made while the model was already working, and nobody had to guess how hard the request was before it started. You have just cut the model off in the middle of a sentence and asked it for an answer anyway. So what do you think it does? It answers. And the technical report says plainly that nobody built this behavior because this ability is not explicitly trained, but emerges naturally as a result of applying thinking mode fusion. The report does not say where the behavior comes from, and admitting that in an interview is worth more than telling a confident story. The report does say in the section on training that for non-thinking samples, we retain an empty thinking block in the assistant's response, and that this ensures internal format consistency within the model. So here's an explanation, and it is ours rather than the paper's. Non-thinking mode was never a second output format. It was the same format with an empty thought inside it, so all the way through Fusion, the model was trained on one fixed pattern where a thought region ends and then an answer begins. Cutting a thought off in the middle leaves the model in a position it has already been trained to continue from. The thing that would settle this is an ablation, which means training Fusion again without the empty block and seeing what changes, and we did not find one. That leaves one question, whether the limit costs you accuracy, and the report plots exactly that, accuracy against thinking budget across 4 maths and coding benchmarks. Accuracy rises smoothly as the budget grows. That curve answers the second half of the interviewer's question because you're not choosing between fast and smart. You're choosing a point on that curve for each request as it is served using one set of weights. So what does that cost? It costs accuracy on the hardest problems, and the report says this itself, that on challenging tasks, the performance in thinking mode actually decreases after these 2 training stages, and that the team chose to accept this performance trade-off to enhance the model's overall versatility. So what do those 2 stages actually cover? Those 2 stages are thinking mode fusion and the general reinforcement learning stage after it taken together, and the report does not separate out how much of the drop belongs to fusion alone. So here's the question again, unchanged, and here's one way to start answering it. Before I answer, I would want to figure out where the cost is actually coming from, because that decides what the fix should be, and if it is the length of the chain of thought rather than which model is answering, then splitting into 2 models and routing between them pays for the same ability twice and still leaves somebody guessing how hard the request is before any work has been done. So my default would be to keep one set of weights and make the amount of thinking a setting at serving time, a mode flag on the requests where the caller genuinely knows the job is easy, and a token budget on the thinking phase everywhere else, because a budget is the only one of those that does not need anyone to guess how hard the request is in advance. The one thing I would want to confirm first is whether a smaller model in your family is genuinely cheaper per correct answer on your easy traffic, because if it is, then routing becomes worth doing, and I would argue the other way. And that is what happens to our request. 13 solutions and 901 tokens becomes a flag or a low limit. The genuinely hard request next to it gets a large budget, and both of them run on one set of weights with nothing in front of them deciding anything. The answer stopped on a question rather than on a recommendation, because the accuracy cost we just named is real and the recommendation depends on it. So what happens if one condition changes and everything else stays the same? That depends on which condition it is, and here is one worth working through. The company stops competing on cost per request and starts competing on benchmark scores at the very top of the range. So which of the architectures we have built would that point to? The answer is 2 separately trained models, and that is not a thought experiment because it is what actually happened. In July 2025, Qwen released an update as separate instruct and thinking models and dropped hybrid mode. The Register quoted the team saying they had decided to stop using hybrid thinking mode and would train instruct and thinking models separately so they could get the best quality possible. There is harder evidence than that secondhand quote, because the instruct model card itself says the model supports only non-thinking mode and does not generate thinking blocks. The flag is gone because there is nothing left to flag. None of that means the technique was debunked because nothing was discovered between May and July. The trade-off the report accepted in May is the same trade-off the team rejected in July. A priority changed, and where did they go? Back to two models, not to a router. There's no classifier in that split because the caller picks the endpoint. So nobody in this story ever worked out how hard the request is in advance because both architectures handed that job to the caller. The question is not settled either because DeepSeek's documentation today lists all three of its current models as supporting both modes inside a single model. That is the point worth keeping from all of this. The question of how much a model should think does not disappear when you change the architecture. It moves. Every architecture here is a choice about who answers that question and when they answer it before the work starts or while it is running. And that choice, rather than the name of a technique, is what the interviewer was testing.